look at our first instance of nonlinear systems, and we'll go ahead and just point this one out up here. It says, consider this system of equations as negative 2x plus y equals 5, which, by the way, this top one is a linear thing here. But we notice down here it says x squared plus 3x minus y equals 1. This is in standard form, but I noticed that if I isolate the y again, which, by the way, what I'm going to do is I'm going to bring both of these terms over here and get negative y by itself. But by getting negative y by itself, to get y by itself, these things that when they went over to the right side became negative would become positive again. But the one over here that was positive would become negative when I turn that y positive. So we've got this thing right here. You notice that this is a quadratic thing. So when we look for the solutions to this system, we have some methods that we can use to do this. One way to do it though is to graph it. And so I just actually want to start with the graphing method. I want you to see here, and I suppose I could put this into, it's called projector mode. You can see, I click on this right here. You see the point 2,9 is on the graph. Also the point -3, -1. So I'm gonna record these right now. If I had a graphing utility, of course, the first thing I do is just go graph it. So -3, 1, and then 2, 9. These are what we suspect we're going to get when we look at this. So it says, how is this different from the systems we've seen thus far? The elimination method is not going to work for us here because we're not going to be able to kick out two sets of variables at once, leaving only behind one. So it's just not going to happen. So elimination method with nonlinear systems is probably a no-go. So we say elimination. We don't want that here. So we're going to have to do this either graphing or we can have to use substitution, which is what we're going to do. It says, how can we easily, though, find out how many solutions this system has without solving it? Always the answer is going to be this: graph the system. Because what we're looking for is points of intersection. So we say points of intersection. Well, you know what? Without further ado, what we're going to do is we're going to use the substitution method here. And so we have this system here, negative 2x plus y equals 5. And we say x squared plus 3x minus y is 1. Let's go ahead and solve for one of these variables in one of these equations. Actually, the one I'm going to solve for up here is y. So we say y equals, when I displace the 2x that was negative, it becomes positive. I get this slope-intercept form of this line right here. And what we're going to do is we're going to substitute that back down in here. Now, the important things to keep in mind are just algebra skills, which mean, when you substitute in for something, you should put in a blank set of parentheses. We are indeed having a negative in front of this, so when you put a 2x plus 5, that certainly makes a difference. So we get this x squared plus 3x minus 2x minus 5 equals 1. We're going to go ahead and combine like terms, so we get a single x minus 5 equals 1. And to solve this, we're going to have to do this by factoring. It's a polynomial, so we'll bring the 1 over here, set it equal to 0, minus 6 equals 0, and I can think of two factors that multiply out to be a negative 6 and add up to be a positive 1 here in the middle, and that'd be a positive 3 and a negative 2. So the first thing I want you to see is this: we get two zeros, one at negative 3 and one at 2. The unfortunate thing for us is this: that means that there are 2 points of intersection. We want to record these. So here are the solutions. Here are the solutions. Make sure you mark these. The thing is, we still do not know the y values of these two ordered pairs. Okay, so what we need to do is we need to re-substitute to find these values. And I noticed that it'd be a lot easier to plug these back into not the second equation, but the first one. So I get this: we get negative 2 times my unknown plus y is equal to 5, where I'm plugging in a negative 3 here. So we say negative 3, this gives me 6 plus y equals 5. That means when x is negative 3, y equals 1. When these two are true at the same time. So we say this is 1. I'm going to put a big fat 1 right there. That's a 1. 1. Okay. There's my 1. And we say plugging in 2, this would have just been a 2 instead, 2. And we would have gotten, a new equation, negative 4 plus y equals 5, which you notice that in that instance we got 9. Okay, so this would be a 9 right here. Look, those question marks like morphed into what I needed. So we have two solutions. So we say that this is a system that is consistent. A consistent system. You've got solutions, and these are independent graphs because they do not have infinitely many solutions, essentially. Okay, so this is our set of solutions right here. Okay, so now looking at this other system up here, we have negative x plus y equals 4. We certainly can graph that, and maybe this is good for us. Good exercise that we could graph this. Let's go ahead and do that. I noticed that the first constraint is linear, so I suppose we could graph this using the intercept method. We say plug in 0 for x. What do we get for y? We get y equals 4. And plug in 0 for y, what do I get for x? I notice that I get negative x is positive 4, so this would be a negative 4. So we get negative 4, 0, which is right here, and then 0, 4, which is this guy up here. And we want to make sure we label this. Seriously, label it, because we're going to be getting into pretty hefty systems sooner or later. So So this right here, we say, now this thing right here, what if we were to get y by itself? It would say y equals negative x squared plus 3. So I know that this is just a quadratic function that's shifted up 3, so 1, 2, 3, okay? And that it opens downward with an a value of -1. So we say down 1, right 1, down 1, left 1. I know that my graph looks like this. So the interesting thing here is this. And notice that they never touch, so we say that this has no solutions. Another thing I want to say about this system is that it is inconsistent because it didn't give us at least one solution. Other things, we could solve this algebraically now that we've seen it graphically. How does this give me no solutions? Let's go ahead and use substitution method again and get y by itself. So this equation would produce y equals x plus 4. We can go substitute this into the other equation, so we get x squared plus y equals 3, where we're going to plug in this expression x plus 4. And then now setting everything equal to 0, x squared plus x, if we bring this 3 back over, we get plus 1 equals 0. This does not factor, and when we use the quadratic method where we say, well, it looks like we have an a value of 1 here, a b value of 1, and a c value of 1, we notice that we get x equals negative b plus or minus the square root of, not easily written here quickly, all over 2a. Basically what I want us all to see is this. If I plug in 1s for all of these, you're going to get some bad news bears going on in here. We say in here you're going to get 1 squared, which is 1, minus 4 times 1 times 1. So we get this, we say x, we have two roots here. We have -1 plus or minus the square root of -3 all over 2, which in other words, you know, if we put an I out front here and make this a positive again, we get two roots. We get -1 over 2 plus or minus root 3 over 2i. And so we'd say these never intersect. They have no real points of intersection, so this is an inconsistent no solution system.